expansion or expansion due to heat, or even thermal contraction, because things do expand when we heat them and they contract when we cool them. We'll talk about metals today because we will and I can. So we all know that metals will expand and contract due to a change in temperature, either up, hot, or cold. So things expand, metals expand when we heat them up, and they contract when we cool them down. That's why we need things like expansion joints on bridges and expansion joints on tracks for the railway, because if the metal expands and there's no joint or there's no place for it to expand into, that causes buckling. Because when you've got expansion, you've got a force and a stress. So things expand and contract due to heat. That delta T just means change in temperature. So when there's a change in temperature, there's an expansion or a contraction. If a metal is heated up, it will expand, you should know that, and if it will contract if cooled down. So for example, here's my stainless steel. Now the stainless steel has got a coefficient of thermal expansion, 18 times 10 to the minus 6. Which really means if this was your stainless steel, we'll only consider, right, in this going that way, you know, one axis, uniaxial expansion. Obviously it goes that way as well, right? But we'll just for now consider going it uniaxial, one way. For every 1 degree C increase, right, the stainless steel will expand by that much meters. So 18 times 10 to the minus 6 meters. Not a lot. So every degree that goes up, it goes up by that much, that way. And say every time we decrease it, it goes down by that much. Linear expansion. So the coefficient of linear thermal expansion depends on the bonds between the atoms of the material. Because not all, this is stainless steel for example, so not all metals have got that number. So this is a constant depending on the metal. Material will expand by a certain length, so delta L is change in length when the temperature changes a certain amount. Change in temperature. So if we've got a change in temperature and we know the length, we can work out the change in length if we know this coefficient of linear expansion. So delta L means change in length in meters. L means original length in meters. Delta T means change in temperature. Now that doesn't matter what unit that's in because it's changed, so it's one take away the other, as long as it's in both the same units. Coefficient of linear expansion is the constant of the material. Here's our formula. So to work out the change in length in meters, because our length should be in meters, due to a change in temperature, we can use this formula. Length, coefficient of thermal expansion, and change in temperature. Obviously, if it's going up in temperature, it's going to be, change in length is going to be going that way. If it's contracting, it's going to go the other way. So that's the formula. Length times by coefficient of the expansion and change in temperature. Nice and easy. So as with direct stress, like we've done before in previous lives, direct stress and strain, a thermal change in length, and this is the change in length due to heat really, that will also cause a thermal stress. So if I squash something with a force, that's direct stress. If I heat something up, it's thermal stress and thermal change in length. Same formula really. So thermal stress is also linked to force and area by this. So stress is force over area. So thermal stress is force over area. Same thing as tensile stress, compressive stress. That's the symbol. So that's stress, thermal stress, just so you know. So stress is force over area, which means thermal stress is force over area. Now, this is why we have expansion joints, because if there's a stress, there's going to be a force. And if that stress can't expand, if the change in length can't go anywhere, it's got to go somewhere. So if we had a wall, say, so this is a bit of metal and it's constrained here, so it can't go this way and it can't go that way. So when we heat it up, it's going to have a change in length going this way and a change in length going that way, say. Thermal stress that way and thermal stress that way. If it can't go this way, it's got to go some way. It's got to expand. And if the force can't go that way, it's got to come this way. So it's going to go like that. It's constrained, so the force in newtons will cause this thing to buckle. Obviously, if these walls can move a bit, right, or we can, expand a bit, then it's not too bad. But that's why you get buckling of train tracks or buckling of metal, because the force has got to go somewhere. So the metal expands, a stress and force will be induced. If the metal is constrained by the wall, the force only has one way to go, up, or it could come down. So thermal stress is our formula for thermal stress. Young's modulus, because really it's to do with, elastic, coefficient of thermal expansion, and change in temperature. So again, thermal stress E, which is Young's modulus in Pascal, coefficient of expansion, and change in temperature. Change in temperature. It doesn't matter what unit you're in, it can be in degrees C or Kelvin, it doesn't really matter, because it's the change, as long as they're both in the same units. So that is thermal stress. And from thermal stress, we can then work out force, because we know this force. We could work out area. Don't forget the area is going to be the cross-sectional area. So that's the three formula really that we use. So for example, a metal bar, 50 mm in diameter and 700 mm long, is heated from 20 to 55. Calculate the change in length, so we need to find that. And the force and stress induced if the bar is prevented from expanding. We'll find the stress first, then we'll find the force. So first things first, the change in length, we know this, we know it's going from 20 up to 55, it's 55 mm in diameter, and it's 700 mm long. Here's some values. Coefficient of expansion is that, and Young's modulus is that. So we need to find the change in length first, which we know is original length times by coefficient of expansion times by change in temperature. So the length is going to be 0.7, just because there's 1,000 millimeters in a meter, so 700 mil is the same as 0.7. Coefficient of expansion is here somewhere, there, and the change in temperature is 55 down to 20. So 55 take away 20 will give you 35. 55 take away 20, just in case. All right. So the change in length is going to be that times by that times by that. Because this is in meters, our change in length is also going to be in meters. If you wanted to, you could keep that length in millimeters and it would come out in millimeters. So 0.7 times by 17 times 10 to the minus 6 times by 35 gives me that, press that. So 416. So 416 times 10 to the minus 6 meters, or 0.4165 mil, which is Tichy. So you could do the same sum, because that really, I mean, I can picture 0.4 of a mil better than I can that. So if you wanted to, you could just, if you just keep this in millimeters, this comes out in millimeters. So 700 times by 17 to the minus 6 times by 35. So there are 0.416, 0.4165 of a millimeter. And if I divide that by 1,000, that will get me into meters. Right. So it's 0.4 of a mil, which is not really much to worry about, I suppose, unless you're NASA. So that's the change in length of the bar, the change in length. Now we need to look at the thermal stress and the force. Here's my formula for thermal stress. And here's my formula for stress. So I can, once I've got the stress here, look, I can then work out the force. So thermal stress first. Young's modulus, coefficient of expansion, and change in temperature. Young's modulus is up here, giga, 9. This here is this here, and change in temperature is the same as it was up there. So put that into calculator. Don't forget thermal stress. Stress is going to be big. So we'll have 90 giga times by 17 minus 6 times by 35. This will give me a big number. So that's nothing wrong with that number. Just you may forget a few notes. If you press ENG, 53.55 times 10 to the 6 Pascal or mega. So that's how much thermal stress. So tick. Now we need to work out the force. So if, for example, it was like this, and it's fixed here, look, so the force can't go that way, it's got to go up, say, because there's always going to be a force. It's just if you constrain it, you know, the force will cause a bit of buckling perhaps. So the force is going to be linked to this. Stress is force over area. Let me have a bit of water. Stress is force over area. We need to find force, so I'll just bring the area up here. So force is going to be stress times by area. We need to find the area. We can do that because it's a metal bar, 50 mm in diameter, which means it's a circle diameter. So the area is going to be pi r squared or pi d squared over 4. Don't forget 50 mm has got to be in meters. So we'll do this, 50 minus 3 squared times by shift pi, divide that by 4. That'll give me that. So there's my area. Obviously I've rounded up a bit there. So I'm going to keep that number in now, make it a bit more accurate, because I know that force is going to be thermal stress times by area. That's my area. I keep that in. I'm going to multiply it by 53.55. So multiply that by 53.55 to the power 6. Gives me 105. So 105 kilo, obviously, because I've used, you know, I've rounded a bit, that's why I got a different answer here, but 104, 105 kilonewtons. That's the force that would be induced due to that change in temperature. So that would be the force perhaps causing this thing to go up or down, buckling. If it could expand this way, the force would be going that way. If it can't, it's going to go somewhere. Example 1, nice and easy. So it's working out change in length, force and stress. That's all we're going to have to do really. Number 2, a copper rod is 12 meters in length and is heated from 10 to 160. Calculate the new length, not just the change, now the new. So that's my thermal expansion. Change in temperature is going to be 150, and there's my length. So we need to find the new length, so I'm going to work out the change in length first, then add it on to the 12. So we'll keep everything in meters. So the length is 12, coefficient of expansion is 18, and my change in temperature is going to be 160, take away 10, which in my book is 150. So 12 times by 18 to the minus 6 times by 160, take away 10. Close that, gives me that. 0.0324. So that's the change in length in meters, because we need to find the new length. Right, that's the change. We need to find the new. Starts off at 12. It's going to go up by this much, so we just add 12. Here, look, add 12 to this, add 12 to this, plus 12. So 12.0324 meters. So if that was a metal rod, copper rod going from 10 to 160, that's the expansion there. How much it would change by, go up. So not much. It's only doing that in it. It's only doing that per change in temperature. So that's the change in length of that one. And then part 2, calculate the thermal stress and the force induced in the bar, in this copper bar, if the diameter is 20 mil on a Young's modulus, and bar has a diameter of 20 mil and a Young's modulus of 210 giga. So again, thermal stress is, there's the formula for thermal stress, Young's modulus, which we know is here. Coefficient of expansion is going to be the same as that. Change in temperature is going to be 150 again. So multiply them together. So Young's modulus is 210 to the 9 times by coefficient of expansion, which is 18 minus 6, times by the change in temperature, which is 150. Give me a thermal stress. It'll be a big number, 56, 7 and loads of noughts. You can use that number, but you may miss a nought out. Press E and G to put it into engineering view. 56 times 10 to the 6 pascals, or 567 megapascalios. That's the thermal stress induced in that copper due to that heat change. We need to find the force now, just like we did up here. So force over area, stress is force over area. So force is going to be stress times area. So I'll work out area. Pi d squared over 4. My diameter is 20 mil. 20 mil diameter. So I'm going to convert that into meters just by doing this. Equals that. We'll square that, equals that. We'll times it by shift pi, and we'll divide that by 4. Gives me this. I have 314. So I've gone up a bit there. I'll keep that number in the calculator because I know that force is thermal stress times by area. From there, look. Just bring the area up. I know my thermal stress is 567 megapascal, so I'm going to leave that in there, make it a bit more accurate, times that by 567 to the 6 equals that, or that, 178 kilonewtons. So 178 kilonewtons is the force induced in that copper bar due to that change in temperature. So that's it really, that's all it is for now. Obviously you can go further with this because the heat just doesn't expand it in one direction, and you know, you can have direct stress and thermal stress combined, so that's in the future but not for this module. So thermal expansion all done.